Hello everyone, I am Emre Koçyiğit and this is the video 3 of Large Language Models Mind Map Introduction. Also, this is the last theoretical video of this video series. Until now, we saw the position of large language models in the language model family in the AI world. And we checked the difference between PLM and LLM, pre-trained models, pre-trained language models, and large language models. And we saw the challenges about LLMs and their powerful sides, the features, important aspects like scaling, emergent abilities. We learned new terms like in-context learning, prompt completion, instruction tuning, and the key techniques behind the LLMs. So basically, we completed this part. And in this video, I want to highlight a few things about the large language models. And I will explain the core architecture behind the LLMs softly. Okay, let's start. Remember, I'm using a survey of large language models paper, this comprehensive survey paper as a major source. And this diagram is from that paper. And here you can see from 2019 to 2020, first part of the 2023, we have different LLMs. We don't have only ChatGPT, GPT, or BART. We have T5 from Google, then we have GPT-3 from OpenAI, and also we have other models from Microsoft, Meta, Amazon. As you see, different models from different companies. And only between 2022 and 2023, we have 27 LLMs. Especially I want to show this diagram because, as you see, we have more models, not only the popular ones. And each month you can see new release from these companies. And the release of ChatGPT is a quite important milestone because it increased the popularity of LLMs. But before ChatGPT, we had a lot of models, as you see. But after ChatGPT, not only the popularity, but also the investment, the all attraction from the companies have been increased. And that contributed to the community a lot. And another important milestone can be accepted GPT-4 because GPT-4 is able to use both text and also the image as input or output, and it responds more safely to malicious or provocative queries. This is very important to remember the topic of alignment of LLMs with human values or reinforcement learning by human feedback. Not only safely, but this GPT-4 performs better than other models in different categories, in different tasks. Remember the diagram in the previous video about the comparison of GPT-4 and other models. Of course, you can see better results than GPT-4 for specific tasks. You can have fine-tuned models for specific tasks, then they can perform better than GPT-4. And another diagram, another popular diagram, this evolutionary tree. And the paper is Harnessing the Power of LLMs in Practice, a survey on ChatGPT and beyond. I will also add the link of this paper to the description. You can check it. And here you can see from 2018 to 2023, we have different models. All of them are not large language models. You can see here we have fast text, GLOW, word-to-vec, or BERT models, or GPT-1. So these are, remember, GPT-1, BERT models. These are pre-trained models, pre-trained language models, not the large language models. But in the evolutionary progress, of course, these are the but remember the architecture of the GPT-1 and GPT-3 they have similar core components, core architecture. Also the BERT model has a similar architecture, which is a transformer architecture. Except for these models, they are all transformer-based models. So here we have 52 models. Of course, now we have more, but in this diagram we have 52 models, and some of them are closed and others open source. They are available. My first and the most important message from this diagram is all of the state-of-art models are transformer-based models. Their architecture, their core parts are transformer architecture. And you can see different colors in different brands. So these colors represent the type of the transformer architecture. So this part, let's say the pink part, reddish part, Bert, Roberta, Albert, they are all encoder only models. And the green part is the encoder and decoder part. You can see Phil and T5, Alexa TM, ChatGLM, and other models. And here, this part are the decoder-only models, and GPT, Llama, BART, and the most popular models are here, you can see. Chinchilla, InstructGPT, they are all decoder-only models. But what is the transformer architecture? What does it mean? Encoder-only, decoder-only. Now I want to explain the transformer architecture briefly and softly. I will not go to details too much, but I want to just show that what is the encoder part and why this transformer architecture is powerful and preferred in these LLMs. Also, you can see here, Llama is an open source LLM from Meta, and the BART from Google, GPT-4 from OpenAI, Jurassic, and Claude, they are all closed LLMs. That is also important to consider. Okay, let's go to the transformer architecture. So this is the original diagram from the paper which introduced this transformer architecture. I will add the link of the paper to the description, you can check. If you want to understand the transformer architecture, you should definitely read that paper. And I will also add one more link which is quite beneficial and explain the transformer architecture. So here you can see we have inputs, outputs, and two core components. So this part is the encoder part and this part decoder. So in the transformer architecture, in the original paper, we have two components, two major components, encoder and the decoder part. And you can see we have some other sub-components like embedding layers, multi-head attention mechanisms, normalization layers, softmax, etc. At the beginning, it can seem a bit difficult to understand or different from the traditional deep learning models like RNN and CNN. Let me simplify the architecture. Here you can see we have encoder and decoder. These are two components, and we have embedding layers and the PE. These are the positional encodings. The models, like in machine learning, in deep learning, traditional models, cannot process raw text. We need to tokenize our text, our inputs, and then with embedding layers, we will produce a numerical representations for each token. But these representations will be vectors. And by these vectors, we can capture the semantic relationship between tokens. So embedding layers are not new in the transformer architecture. We have word-to-wake, GLOW, fast text models, and they can produce word embeddings. And the PE, the positional encodings, they add positional information for each token. In RNN, in traditional process, we have a sequential process. Therefore, we don't need to add positional information. But here, if you look at the details of the architecture and the flow, you will see that the models need to know the position of each information. And here, inside the encoder and decoder, we have multi-head attention mechanisms. So other parts, the feed forwarding part, normalization layers, softmax, these are all easy to understand, and they are not completely different from the previous deep learning models. If you are familiar with the deep learning architecture, you will easily understand it. But the multi-head attention mechanisms and the masked multi-head attention, of course, these are not available in the traditional deep learning models. So while the attention mechanisms existed before the transformer architecture, the way this self-attention is employed in the transformer is a novel and a crucial aspect. So these multi-head attention mechanisms allow for capturing complex relationships between words in a sequence. So the idea of using multiple attention heads to capture these different relationships, the complex relationships in a parallel, was a novel contribution here. So it allows parallelization, and it allows the model to attend to various aspects of the input. You can imagine with these attention mechanisms, you can have different perspectives, different views, and it enhance the generalization ability of the models also. Here in the decoder component, we have masked multi-head attention. This is quite similar with the multi-head attention in the encoder, but the use of masking to prevent future positions from being attended was a novel technique in this decoder only. It is crucial for especially autoregressive generation tasks like language modeling and machine translation. So basically, when we say encoder only, we have only this component, and decoder only has this part. But we have also encoder, decoder, large language models, so they have these two components. But the innovations, the real power of the transformer architecture actually is based on this multi-head attention mechanism. Details of the transformer architecture, other parts, the attention, matrices, query, key value, these are all important topics, but I don't want to go to details in this video because this is not about the transformer architecture, but about large language models, and this is just a starting point for you. If you really want to study on LLMs, you should firstly understand the transformer architecture, because as you see in the previous figures, we have a lot of LLMs and they are all based on transformer architecture. To sum up, I want to highlight this. So transformer architecture provides parallelization ability. So with self-attention mechanisms, with these multi-head attention mechanisms, so these mechanisms allows for parallel computation. So this is very important because it reduces the training time, it increases the training speed. And remember, when you have more data, more parameters, the cost will be higher, you will have longer training times, but when you have parallel computation ability, that will change the training time, it reduces it, and it's very important. And another important point, scalability. So with this transformer architecture, we can use large data sets and large models. In the pre-trained models like BERT or large language models like GPT-4, Pine, Lambda, we have huge models with billions of parameters and massive data sets. So this architecture is usable to capture the complex patterns, and since we have more data, more models, and with the abilities, the models can generalize better. This is quite important. And another one is long-range dependencies. So in the RNN, LSTM, GRU, we have still a problem of remembering. But in the attention mechanism, it allows tokens to attend any other token in the sequence, regardless of distance. We can check the relationship between the last token and the first token of the sentence, of the sequence. So thanks to this ability, it can capture both local and also global dependencies through the input. And the last but not least, of course, transfer learning. So you can pre-train models with massive data, you have parallelization ability, you can have more complex models with millions or billions of parameters. Then, for special problems, for your special tasks, you can fine-tune the model. Today we have different type of transformer architectures, and for example, GPT-4, Lambda, Pine, these are all decoder-only models, and of course they have other characteristic differences inside their architectures, but we are not able to see all differences because they are not open source. But to see more details, you can check open source models like Llama from Meta. Okay, this is the end of the theoretical part, so part 3. The next video will be hands-on video. I will try to show a few examples in Python, and in each video I will use different models or different techniques. And I hope these videos will be helpful for you for your research or project, and you can build your own application by using LLMs or fine-tuning LLMs to solve different real-life problems.